Namaste to everyone. I welcome you all in my YouTube video channel. Today, I will deliver lecture on complex analysis, chapter complex integration, lecture number 1, in which I will give the concept of some basic definitions related to complex integration. Let O be the origin, OX be the x-axis and OY be the y-axis. Let P be a point in this xy plane. Let this point moves with respect to time. As time increases, the point moves in this xy plane. Let at any time the position of P is Q and its coordinate be xy. This point may be also represented as Z equal to x plus iy in terms of argand plane. As the point changes its position, that means the value of x and value of y also changes with time. Therefore, x is the function of time and y is also function of time. That is, z is also function of time. This z equal to zt represents the curve. Therefore, z equal to zt represents a curve on argand plane. Here we see that z depends upon time t. Time is a parameter. If we take here set A and set B the collection of points means z. For t1 we get here z1. For t2 we get z2. That is, z depends upon time t. We write here z t1 equal to z1, z t2 equal to z2. So, locus of the point changes its position, it makes a curve. If zt1 equal to zt2 implies that t1 equal to t2, then z is 1 function. And in this case, the curve is said to be a simple curve. Now we define what is simple curve. A curve z equal to zt, function of t, z is the function of t, is said to be a simple curve if a function zt is 1, that is, no two different values of t correspond to same value of z. Now we define simple closed curve or Jordan curve. A curve z is a function of t is greater than equal to a, less than equal to b, is said to be a simple closed curve or Jordan curve. If no two different values of t other than a and b correspond to the same value of z, that is, only ZA equal to ZB for A not equal to B. For example, let here P be a point. This point is xy, that is, at this point value of z is x plus iy. This is x-axis, this is y-axis, and this is the origin. In the Jordan plane, this point is z equal to x plus Iy. If this point moves, that is, time increases and it come back again after some time, here P. Let at the starting time t equal to a, and after moving this reaches to P, at that time t equal to b. Here a not equal to b because starting time is not equal to final time, and we see that at starting time t equal to a, z equal to x plus iy, and at final time the value of z is x plus iy. That is, at initial time and in final time value of z will be same, but other than this time, for two different time the value of z are not equal, and this type of curve is known as simple closed curve or Jordan curve. Now we define rectifiable arc or curve. Let an arc C, which is denoted by AB, be defined by z equal to function of t, where z equal to x plus iy. Therefore x is function of t and y is function of t, and t is greater than equal to alpha, less than equal to beta. Let us consider a partition P1 of closed interval alpha beta. The partition P1 is done with the help of points T0, T1, T2, Tn. Corresponding this partition, the arc is divided into n sub arc. Let any particular sub arc is denoted by Ck. This is the arc joining zk minus 1 zk. For example, C1 arc is the arc joining z0 and z1. C2 arc, the point joining, that is arc joining z1 and z2. So we get in this partition n number of subarc. Let us join each of these points z0, z1, z2, z3, z4 zn to the next point by straight line. For example, we join z0, z1, here z1, z2 by straight line joining. In this way we get a polygon curve. This is polygon, straight line. These are straight lines. So this is called polygon curve. The length of this polygon curve corresponding this partition P1 will be sigma k equal to 1 to n modulus of zk minus 1. Since we know that if this is point z1 and this is point z2, then length of z1 z2 straight line is modulus of z1 minus z2. Similarly, we may find the length of these straight lines z0, z1, z1, z2, z2, z3, and if we take sum of these lengths, we get this value. This is the value corresponding to partition P1. In the similar manner, we may get different types of partition with the help of different points, other partitions. In this way, we may get other partitions with the help of other points, not Z1, Z2. Here we take any point, here we may take any point. In the similar manner, we get different partitions. And similarly, we may get different value of the length of the polygon curve corresponding to that partition. If we take supremum of these lengths, and if that is L, a finite quantity, that is L less than infinity, then the arc AB is said to be rectifiable arc, and L is called length of the arc C. Now we define neighborhood of a point. Let Z naught be a point in the domain of a complex function, then the neighborhood of this point is a set consisting of all points which satisfy an equality modulus of Z minus Z naught less than epsilon. This means this represents the points inside the circle with radius epsilon and Z naught as center. These points are, collection of these points are neighborhood of Z naught. Neighborhood of Z naught consists of all points within the circle but not on the circle. Here epsilon be the radius of this circle, which is very small. Now we define interior point of a set. A point Z naught belonging to a set S is said to be interior point of S if there exists at least one neighborhood N of Z naught, if N is subset of S. Exterior point. A point Z naught not belong to S, domain of the function. S be the domain of the function, is said to be exterior point Z naught to S. Boundary point. A point Z naught. A point Z naught is said to be boundary point of S if every neighborhood of Z naught contains both points of S and points not belonging to S. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.